Hello, this is Michael Levitt again. This is now part 3 of the series of short videos describing growth and fitting of COVID-19 data. This talk is about fitting data. Again, Michael Levitt from Stanford Medical School. Just a quick word about fitting data. It turns out, that in some ways, all of machine learning is fitting data. In machine learning, we fit the data with a function that is a composite nonlinear function. We don't actually know what the function is, but we know it fits the data well, and therefore can be used to do the sorts of predictions that machine learning and AI can do. In this case, we're going to fit the data by looking at the data and thinking what function would best fit the data. So we're going to start out with 2 examples. It turns out in order to find good examples, you need situations where there's generally a single outbreak, but we'll see, in fact, that these are quite hard to find. So South Korea, so if you actually look on the scale here, this is the number of cases on a log scale. And what you'll see is there's a bump and it stops, another bump and it stops, another bump, and then a 4th bump. And because each of these are on our log scale, here we went from 1 to 6, here we went from 6 to 30, here we went from 30 to about 1,000, and then we went from 1,000 to 10,000. So we're going to try to just fit this last one here by essentially taking these numbers, subtracting away 30, not worrying too much about this piece, and getting a fit to here. Now, if you remember, this kind of curve behavior is what we saw for the Gompertz function. So in this particular exercise, we're going to try to fit with the Gompertz function. We could easily have fitted by the sigmoid function, but I wanted to try to make a point here. So let's just first look at the data. One thing that's very, very important in anything involving biology is look at the data. Biology is very tricky, and data is not what you think it might be. So now we get to look at the, oops, sorry, I just showed the fit, but it's not important. Now we're coming to South Korea, looking at the data, no smoothing, the raw data coming out of the Johns Hopkins database. We're first going to look at just the number of new cases. It goes like this, you can see it's curving. Started out quite high because in South Korea, no one recorded anything until there were about 60 cases. Again, this often happens. Now, what does the slope of this function look like? Wow, it's going down like a straight line. Remember the Gompertz function? Finally, the number of new cases. This is shown on this axis on a linear scale. This is very noisy because the number of new cases is taking 2 values of the total cases and subtracting them. But again, it goes up and comes down. So what we're going to do on the next slide is try to fit this function. Okay, these is the data again. We're now going to fit this with Gompertz, and this is the fit. You can see it doesn't actually fit this piece because this was an initial outbreak that we basically should have fitted separately. Now look at this data. Well, as you might imagine, a straight line goes through it. These are the actual numbers of the fit. This converged at 8,500 cases. K is the slope of this. It's actually a rate. And K equals to 0.22 means that this function decreases to 1/e of its value in about 4 days. If this was 0.25, it's between 4 and 5 days. So there's essentially, this is telling you how rapidly this line goes down. And finally, the number of new cases, exactly the same raw data. This is the fit. And again, you can see that it's asymmetric. When it peaked here, it had not done with the cases. Now, in South Korea, there were additional cases here. We just fit it up to this point because infections often continue. We're looking at the dynamics of a single outbreak. Well, that's South Korea, one of the early cases. Let's look at another case, New Zealand. So New Zealand also actually had multiple outbreaks, but only 2. There was an outbreak here, where they got from 0 to 6 people, got it under control, but then another one started here. And again, you see this familiar curved shape. You could probably put a straight line through that, but you can put a straight line through many groups of 3 points. And that's the fit to this piece here. In fact, even this piece here is in fact a separate outbreak. So here's the data, the number of new cases, total number of cases on a log scale, the slope of this line, you can see it's going into the ground like a straight line, very, very significant. Had growth been exponential, these points should have been along here. And then the number of new cases, and again, a nice peak. Of course, this is noisy. This is not a double peak. Data is very noisy. Same thing fitted. First, we fit the total number of cases on the log scale. good fit there. Total number of, slope of that curve, a good fit there. And finally, the number of cases, and again, a good fit for unsmoothed data. In this case, the slope is a little bit less. This line slopes less. In fact, it gets down to 1/e after about 7 days. So after, you can see it's decreasing, goes down by a factor of 10 in about 2 weeks, but it gets down to a factor of e in about 7 days. Okay, so what are the conclusions of this fitting? So basically, we see now, by just looking at the data, that from the very first confirmed case, the rate of growth of COVID-19 confirmed cases, it's not constant. Thus, growth is never exponential. So the terrible thing we're fearing is not true about a single outbreak. Instead, the constant exponential rate is decreasing rapidly. And although the initial growth rate is very fast, it's decreasing at an exponential rate. How is this possible? We'll come to explain this in further talks and what I write. And how does it affect the control of the COVID-19 epidemic? And I believe there's some important lessons here. Thank you all very much.